All right. Shall we start?
I guess, yeah. Yeah, I think we're starting.
All right, perfect. Okay, so welcome all to the second part of the morning session. We have two talks, 45 minutes each, one on QBF and one on Isomorph-Free Generation of combinatorial objects with SAT modulo symmetries. And Stefan will tell us more about this.
Yeah, please. Thank you. Also, many thanks to the organizers, as usual. Very nice being here, connecting with everyone. Yeah, so I'm talking about the generation of combinatorial objects using SAT. And so this is something that's in combinatorics, often questions can be phrased in this way. Is there a graph or some other combinatorial object with a certain property? Does it exist or not? Yeah, what combinatorial objects are there? Graphs, hypergraphs, matroids, etc. Everything that I'm considering things that are like finite structures. During the talk, I will mainly focus on graphs, but later on with the applications, I will also have a few things about other objects. And there are variants of it. We want, for instance, to enumerate all objects of a certain size with our property X. Extremal properties, extremal problems in extremal combinatorics. People are, for example, interested the largest number of edges can a graph with n vertices have where the graph is a certain property. There are books on extremal combinatorics, but also counterexamples for conjectures, that we can at least show that the conjecture holds up to a certain size of objects, or maybe ultimately show the conjecture in general, because sometimes we know that from a certain size onwards, the conjecture is true. There are some theoretical proofs, but the small examples, they basically often contain this really difficulty where this more general asymptotic reasoning is not grasping. Okay, what is now this isomorph-free generation? So the number of objects, of course, explodes very quickly. So the number of graphs with 10 vertices, I think it's already like a billion. And so to at least keep this explosion to some, it's still exploding, but let's say it explodes a little bit slower, is by means of canonization. Because every object, you have many isomorphic objects that basically you only need to have, among all these isomorphic copies, you only need to consider one of them. And one way is canonization is a mapping alpha that maps to every object like a unique element of its isomorphism class. And we only want to generate objects that are canonical, so that map to themselves. For instance, here we have two graphs, but they are basically isomorphic by this mapping, this isomorphism here. We only need to have one of them. And there are many ways of canonization, and a popular one, and the very natural one, is by you look at the adjacency matrix of the graph. So you have vertices times vertices, and a 0 if the edge is missing, a 1 if the edge is there. And then you associate with this adjacency matrix a long string where you just concatenate all its rows. And if you now order these objects by lexicographically along their adjacency matrix, you have a total ordering. And here, for instance, you can see the left one is smaller than the right one. And therefore, in the ordering, we can exclude the right one. And now for connected graphs, here is just see the combinatorial explosion. This is without considering this isomorph-free generation. And here you see we get it's growing slower. So for 10 vertices here, this is already crazy. You can't check something one after one. Here, that's still kind of doable, maybe even 1 million. Then it also here it starts getting difficult. And there is like a very standard tool people in combinatorics use called Naughty, introduced by Brendan McKay more than 20 years ago, where you can generate objects like graphs modulo isomorphism. And so you, for instance, you can list all connected graphs with 10 vertices. It gives you this million of graphs. And there's also you can use some restrictions. You only want to have cubic graphs, for instance, where every vertex has a certain degree, then you can incorporate this into this generation. Then it maybe goes for a little few more vertices higher. But it's still, if your property you're looking for is a little bit more advanced, then you can't build it into a Naughty. And then you need to do a generate and test method. So you generate then all these canonical graphs on n vertices, and then you test your property that you're looking for, and then you get the result. But of course, then if the number just of these objects is too large, then you can't do this. And therefore, there exists a SAT approach. We can do this with SAT, and we can kind of avoid this generate and test. The idea is we combine the generate and the test in one process. We can express our property in a propositional formula, where, for instance, for graphs, it's very natural for every edge of this graph that we don't have already. It's like this graph we are looking for, but we have variables for every edge, and whether there's an edge between vertex I and vertex j, this variable eij is true or not. And so by expressing now our property in propositional logic, we can now look whether this formula is satisfiable, and if it's satisfiable, we have our object that we are looking for. And now we can also use auxiliary variables to maybe this property we can't define just on this edge variable, but so we have two sorts of variables. Now the idea is this: we still have we have now our formula fx, which says there exists a graph on n vertices with our property, and the graph is minimal with respect to let's say the lexicographical ordering. And then we feed this into a SAT solver, and then we get our result. So this would be perfect if it works like this. However, there is a caveat, because it's not known, this complete minimality check, to express this with a polynomial number of clauses. So there is, people have tried the following, which works not too bad, to have a relaxed notion of minimality. For instance, this here would say that when we swap any two vertices with a permutation that only swaps two vertices, we shouldn't get a lexicographically smaller graph. This we can express with relatively small number of clauses, and it would at least filter out some of the isomorphic copies. But of course, for a general automorphism, it could swap basically around all the n vertices. So it's only helping a little bit. So this works for instance, Kodish et al. Used this with some good results, but still only a small fraction of isomorphic copies is filtered. Now the question is, can we still use SAT but do better and filter more? And therefore, this was the static approach, because we have a static encoding of this minimality. But now this would be a dynamic approach. So here again, we have propositional formula that expresses our property, but just this formula, that's the only input to the SAT solver. But now we use a propagator. So whenever the SAT solver finds a model, or maybe earlier when it already has decided of some of the relevant variable, it asks an external tool that looks whether this is canonical or not. And if not, a clause is learned and feed back into our CDCL. I omit CDCL. I'm here always talking about CDCL SAT solvers. And only then when the solver finally comes to a solution, then it's canonical. And actually, many people have already used this in some way or the other. Maybe two systems, CDCL Sym or SAT plus computer assistant. No.
Computer algebra systems.
Computer algebra system. Thank you. Are maybe two famous tools that have been developed in recent years. And here I'm not talking about our version of it. SMS, SAT Modulo Symmetries. If you have attended yesterday's talk by Katalin, she has already mentioned it. So what is SMS? What is different with SMS from these other dynamic systems? The idea is here that what we send to our propagator is a partially defined graph G. And I think this is an interesting combinatorial object, which I have not seen studied somewhere else, but it's very natural because like when you're working with, we all used to work with partial assignments. We always know for our formula, the SAT solver, of course, not all the variables are assigned. We have some assigned to true, some assigned to false, and there are some undecided variables. And now we use the same thing now for a graph. We have some edges, we know the edge is here. Some edges, we know they are absent, but then there are some undecided edges. And on these edge variables that are mentioned in this formula, we usually, when in the middle of the solving, they will represent a partially defined graph. And now we send this partially defined graph to our check of canonicity. And now here, because it's only a partially defined graph, we need to figure out whether we can extend this to a fully defined graph, because at the end, we want to have a fully defined graph that is canonical. And if not, we learn a clause. Now, this works basically like this, but how to do this exactly, it's not so straightforward. Here, a little bit more on partially defined graphs. So here, just we can draw it this way, that like this dotted edge is an edge where we don't know whether it's there or not. And also the adjacency matrix is very natural, that we now have also a third symbol. We put a star at these places where we don't know whether the edge exists or not. And yeah, and by the way, this there's a very natural partial order on these partially defined graphs, where we can say that one graph is smaller than the other. So the larger one has basically more edges decided that were undecided on the smaller graph. And so in this ordering, the minimal element is the graph where everything is undecided, and the maximal elements are all the fully defined graphs over the same vertex set. And we write here x of g for the set of all fully defined graphs that g can be extended to. So for instance, for this example here, we have like for every, we have 2 to the number of undecided edges, many fully defined graphs. Good. So the ideal solution in our method would be when we send this partially defined graph to the minimality check to find out or to reject the current branch if G is non-canonical in the sense that none of these graphs, fully defined graphs, G can be extended to is canonical. So this would be ideal. However, when we, or this is just an equivalent statement, for all h in x of g, there is a permutation pi such that pi of h is smaller than h. So that means h is not canonical, right? I just write this here because we will use a very similar statement on the next slide. But this is extremely difficult to check because there is an exponential number of extensions of our partially defined graph. And for each extension, checking this minimality, there's no algorithm known other than in the worst case, you have basically to go over all n factorial permutations. So we have kind of a problem that has two components that contribute to its complexity. So therefore, it's kind of hopeless to do this as it stands here. And even if we had it, would be a problematic because we can't have a certificate if you later on want to give a proof why, let's say, no counterexample exists, and we use a lot of this kind of minimality checks, then they can't be represented directly by some kind of certificate. But our solution is that we have a slightly weaker form of canonicity for partially defined graphs. Because in this weaker form, we reject the current branch of K, which we now call certified non-canonical, if there is a permutation pi such that pi of h is smaller than h for all fully defined graphs, G can be extended to. Now, if you look at this, I think, wasn't that the same thing as one slide earlier? No, we switched the quantifiers. So in the general thing, we say for every h, there exists a pi, but now we say there is a pi such that for all h. So it's a weaker form because the same permutation should now show the non-canonicity of all the graphs in XG. And this is now the thing that we use. You can so now it's weaker. Is now not a full symmetry breaking? It's still a full symmetry breaking because ultimately, if G becomes a fully defined graph, for fully defined graphs, these two definitions are the same. So sooner or later we will catch on and filter all non-canonical graphs. And then once we have determined that this is non-canonical, then for our partially defined graph, it's now easy to define a clause which just for all defined edges. So we have a disjunction which says at least one of the defined edges should not be there, or at least one of the non-edges is there. So we just have a negation on the partially defined graph. And this is the clause that we learn. Because this forbids now all graphs, even all graphs G prime that are larger in this ordering. However, we can even do better. We can even find a smallest graph in this ordering that is below G, and for which pi is still a certificate. So we can get a little bit more even out of it, because we want to learn a clause that is as small as possible. And we call this smallest graph a G pi obstruction. Okay, now this is the picture we have now. We have here the partially defined graph. We fit into our check, and our check of canonicity, our algorithm that we call mean check. For this, we can show a certain completeness. We can show that our minimality check finds a certificate pi, this is this permutation, and such a G pi obstruction H, if and only if G is certified non-canonical. So with respect to our weakened form of canonicity, our algorithm is complete. Yeah.
So I sort of went a bit quickly. So what do you mean smallest in the blocking clause?
The smallest, so you have
in terms of
this partial ordering that we have on this partially defined graphs. So we can basically, when we go in this ordering, this square-shaped smaller sign, we can, from this G that we send to the propagator, we might find an even less defined graph that is still an obstruction.
It's sort of a lifting of the blocking clause, essentially.
Yeah, there are some things. There are some edges that are stable because the permutation either fixes the edge or just swaps the endpoints. There are some things that basically don't matter really, and that we can remove.
I still didn't understand this point. So I understand how you determine that it's non-canonical, the G, the partial assignment, but you're saying that, and therefore you would generate a blocking clause, which would just block that partial assignment, correct? But you're saying something more actually. Can you go back a couple of slides? Sorry, where you talked about minimizing.
Yeah. Here it is.
Yeah.
Yeah, it's just we find from this blocking clause we can in some cases find a subset which is still a valid blocking clause.
How do you do that?
I show it in a few slides.
Oh.
Okay. Yeah, I will go into this because this algorithm is quite central, so I will spend a couple of minutes on it. And for this algorithm, a very fundamental concept there is what we call an ordered partition of the vertex set. So the ordered partition is, as you would guess, you have a partition of the vertex set into, let's say, V1 to VR equivalence classes. But usually for a partition, you would have curly brackets because for a partition, it doesn't matter. The partition doesn't order the equivalence classes in some order. But here we have this linear ordering. And such an ordered partition represents a set of permutations. For instance, this ordered partition of the numbers 1 to 3 correspond these two permutations. So basically, we have like number 1 goes from 2 or from 3, or we can swap the 2. But 1 and 2 must be the images of the first partite set. And then for the second one, only 1 is left. Or if you can also just take this general definition here. But this is now a compact way of representing a set of partitions. And our algorithm now works the following way. We start with the ordered partition where everything is one big equivalence class. And then let's say with 10 vertices, and then we refine it, and we get singletons at the front. And the number of singletons grows. And so to speak, in our adjacency matrix, can also think of fixing from starting from the left top corner, we fix more and more vertices. And it's a branching algorithm. So we make some decision, and then we might backtrack. And the important thing here is the propagation, which I want to illustrate with this example. So this is our adjacency matrix. And here we start with this full ordered partition. Now, maybe we make the first decision. We map 1 to 1, so we keep 1 fixed, which means now 1 becomes a singleton. And the interesting thing, and I think there are also the power of this algorithm, this min check algorithm, is now the propagation, because from this one decision, we get now a lot of other decisions for free. Namely, if we look here at, so we now know number 1 is fixed. Now we look at the other vertices, whether they are adjacent to 1 or not. Now we, for instance, see that the vertices 2 to 5 are non-adjacent to 1. Then 6 and 7 we don't know, and 8 to 10 are adjacent. So in our, because we want to have something that's lexicographically minimal, it's clear that we have to put now those non-adjacent vertices first. So 2, 3, 4, 5 come now in the next equivalence class. The adjacent ones, 8, 9, 10, come at the last. And those that we don't know, we can fix because they can't be stable, and therefore kind of an adversary can always come up with a way of deciding these edges so that the ordering is not minimal anymore. So we have this propagation, and then we go on. Now the next thing, we now want to split this set here. So the first possible choice would be to decide 2 is mapped to 2. 2 becomes a singleton, and again here the propagation would now say we have to split 3, 4, 5. First 3 because it's not adjacent to 2, and then 4, 5 because it's adjacent, and something similar happens here at the last set. Okay, and so forth. And now let's assume we are unsuccessful in this branch and we backtrack. Now here, instead of assigning 2 to 2, we assign 2 to 5. We have now to look at this row here. And again, we do propagation. And here it turns out, and I will show you in the next slide why, we have a certifying permutation found. Because when we look here, and pick any permutation now that is represented by this ordered partition, and if we now look at the permutation of this partially defined graph, we see that up to this circled place, they are basically the same, but now get here a 1 and here a 0. And therefore, we know that G is lexicographically larger than phi of G. And we have found our certifying permutation pi. And now the graph that we know, the obstruction graph, would now consist of basically every edge that is defined in this block here. But we can omit, we don't need to take everything, we can omit these stable vertices where any permutation would basically keep these vertices stable. And we call this, by the way, an indicator pair, this particular like 2, 6, these coordinates of this first cell where we get this discrepancy is an indicator pair, and we can now translate this partially defined graph into a closed entire. Okay, now yeah.
Your order partition is similar to the order partition pair that we have in our SAT symmetry detection. Are you aware of that?
No.
Okay, we can talk later.
Okay. Yeah, I'm sure these order partitions will have popped up somewhere else. It's a very fundamental thing. Yeah, in the worst case, for the performance, in the worst case also, this algorithm could might need to consider all n factorial permutations, but in practice, this worst case is rarely met. But we can also monitor if the minimality check is taking up a big fraction of the overall time, then we can also weaken and say only every kth time a decision on an edge vowel is done, only call the min check then, or delimit the number of recursive calls. But we can still guarantee isomorph-freeness if we run a min check at the very end of the process. Now the implementation, we implemented this in C C++. We have variants for graphs, directed graphs, matroid hypergraphs. And originally, the hosting solver was the Clasp ASP solver. It was at this stage very nice to have something with a well-developed interface that worked quickly. We had the prototype running quickly, and it served us for more than a year. Now, since recently, this Cadical interface, Katalin talked yesterday about it with the IPA syrup interface, is now in some cases quite faster. So that's great. Now this gives the SMS framework also a big boost. And we also have a Python wrapper where we can quickly test some graph properties from the command line. Okay, now for applications. So we have quite a number of applications, and I'm trying to show you here just a few ones where maybe I can't spend 10 minutes introducing you to the combinatorial context of the problem. So I will be here a bit superficial. There is one of the first things that we tried was related to the Simon-Murty conjecture. It's about diameter 2 critical graphs. So the diameter of a graph is the longest distance between any two vertices, and a graph is diameter d critical if by deleting an edge makes the diameter increase. And people in the combinatorics were interested. It goes back to the 1960s to Erdős to study the structure of diameter d critical graphs. And the Simon-Murty conjecture states that the number of edges in an n-vertex diameter 2 critical graph is exactly a certain value which is attained by a complete bipartite graph. And so we could, maybe I show you just a table, but maybe it's not getting too boring. This is when we enumerate all diameter 2 critical graphs, this has been done with Naughty not too long ago. But with Naughty, you can enumerate all graphs basically up to n vertices, and then you check whether it's diameter 2 critical or not. But now with SMS, we could enumerate all the diameter 2 critical graphs up to 13 vertices. Here is maybe also as a comparison. Here, would be the static minimality check where we only swap two vertices. What I explained earlier. And you also see that at the beginning, okay, it works quite well, but then there is a certain place where just the number of graphs becomes too large because it's not a complete filtering. And with SMS, we can go further. Here in parentheses, you see also the percentage of the time that's spent on the minimality check. But just for the conjecture, we don't need to enumerate all graphs. We can just give a bound on the number of edges and show unsatisfiability. So basically, there is no output, no graph is put out. And there we can even go to 19 vertices. Yeah, here we also used some lemmers that on the degrees of the graphs. Yeah, to save time, but you see there's quite some potential on the system. I think what's very important is that we can also produce proofs. So even if we just verify some results that have been achieved with Naughty, Naughty can't produce a proof. But here, because our system is based on CDCL, we can produce DRAT proofs and we can, like an independent algorithm could check whether our results are correct. And also we have now these special clauses that we get from the minimality check. But because we have this minimality check that uses this certified non-canonicity, where we have this permutation pi, our algorithm found. So we log also this permutation pi. And so for all of these special added clauses, we can also have a very lightweight verifier that after a successful run can verify that every these certificates is indeed a certificate. And so we can basically use a DRAT proof for the whole process, where both the reasoning of the solver, but also the minimality, these blocking clauses are verified. Good. Yeah, I think I will skip the Ramsey sets because I want to use a few minutes on planarity. That's something that we relatively recently added to the SMS framework. It's the computation of planar graphs. So when is a graph planar? A graph is planar when you can draw it on the plane without crossings. So this is the complete graph of three vertices, of course, planar. Also a complete graph on 4 vertices is planar. Here it's just, sorry, that was the wrong slide. That's the better one because I wanted to show you that just by drawing it differently, you see this is planar. However, K5, as long as you try, you won't be able to find the planar drawing of K5. So K5 is not planar, as also the bipartite graph on 3 plus 3 vertices also not planar. And actually, these two graphs, K5 and K33, has some prominence because they are the so-called Kuratowski graphs. Famously, Kuratowski showed that a graph is non-planar if and only if you can find the subdivision of one of these two graphs as a subgraph. And also the most efficient planarity checks work by trying to find such also called topological minors of the graph. And now we implemented this with another propagator. So you can't, the non-existence of these subgraphs, you can't encode with clauses, but we just ask externally the same time when we call the minimality check, we also call this external algorithm that looks for these topological minors. And if so, we know that it's not planar and can cut this branch. We also tried other planarity criteria that are positive, that you can encode with clauses, but the performance was quite, I'll show you a table. Yeah, this is now the process. We have the minimality check, but also the Kuratowski criterion. Yeah, here's something on planar Turán numbers. We see here Kuratowski criterion and the other one, the ordering criterion, which the static SAT encoding, you see that the Kuratowski, the lazy Kuratowski encoding works significantly better. Yeah, sorry, I didn't give you the detail. What are these planar Turán numbers? But they are like in combinatorics, people are interested in studying those. And maybe just because it's such a nice problem, the Earth-Moon problem was formulated by Ringel in 1959. Because you all know a planar graph famously can be colored with 4 colors. That's the 4-color theorem. And 4-color theorem was also the first proof that was computer-assisted proof of a major mathematical theorem. And Ringel asked, what is this 4-color theorem comes also from map coloring. what is if every country on Earth has a colony on the moon, and now we want to color the moon map with the same colors as the Earth map. So every country on Earth gets on the moon, the colony moon gets the same color. How many colors do you need? And it's also, some people said it's harder than 2 4-color theorems. And it is only known that this number of colors is between 9 and 12. The lower bound 9 is due to Solanke, who came up with this graph, which is a so-called biplanar graph. You can partition the edges into 2 sets, which gives you 2 planar graphs. You can think of this graph as an overlay of 2 planar graphs. And these are the corresponding map colorings. I see I need to come to an end. And here we encoded this. We needed to extend SMS to digraphs so that we could encode this partition of the edges into, let's say, red and blue edges by means of encoding them in terms of a directed graph. Either you have this diagon or just a simple edge. And we could now show that the Solanke graph is optimal in the number of vertices. We could exclude several other cases where colorings or chromatic numbers that would contribute to the Earth-Moon problem do not exist. It's also a general theorem. Okay, hypergraphs, matroids, I skip just quickly the summary. I think SMS provides a powerful framework for combinatorial problems. It uses the power of CDCL solvers, generates DRAT proofs for verification. We have applied it to many different combinatorial objects, and maybe last but not least, maybe 3 avenues for further exploration. Can be improved minimality check, maybe because of this propagation, maybe a constraint processing approach could help and do a little bit more propagation there. Combining SMS with static symmetry breaking, which currently is not working well, but we would like to get this working. And finally, because some of these combinatorial problems you can't formulate just with an existential statement, but it's more like a QBF statement. Would be nice to extend SMS to work also in the context of QBF. Yes, thank you.
Thank you.
I have an idea for how to make static symmetry breaking work. This came from a student of mine just a couple of weeks ago, because we tried symmetry breaking with SAT. And for static symmetry breaking, you have to assume a static ordering of the assignments, right? Mm-hmm. And you create static breaking predicates. And they may actually add clauses that are at odds with the branching heuristic of the solver. So he fixed the ordering in the solver to be the exact static order, the same as the ones that you use to create the breaking predicates. And he said, I said, so did it work? He said, it's better than not doing it. But so, because, you know, the static breaking requires a particular ordering of the assignments, and then the SAT solver goes and does something different. And so whatever you add to the solver becomes kind of baggage that doesn't help with breaking symmetries during search. So you might
but I'm not sure how this would be consistent with the minimality check. That's the problem, because static symmetry breaking, of course, that works. But the issue here is how can you work it in conjunction with this dynamic minimality check?
But the solver is actually doing search during that minimality check, right? Mm-hmm. And it's branching basically based on conflicts or something else. Mm-hmm. And it might choose the ordering of the branching to be different from the symmetry breaking predicates that you may have added to the solver. And so if you force it to use the same ordering of the variable of the, we can talk about that offline. Yeah. But it's again, I don't understand it, but it's a great idea. But then when you add it to a CDCL solver, it doesn't work very well.
Let's have a final question there.
So when you get so many outputs, I don't know. I never do that with a CDCL solver because if I have something with 10,000 outputs, I have to add nine. I have to in order. I mean, I have to add another clause saying, "Don't give me the other 9,000 that I've already seen." Does that actually work well? I mean, for getting for problems with that have lots of answers, I always use a different set of them.
Yeah. So I think the question is about when we say we enumerate, we calculate the total number of all graphs with a certain property. Yeah, we do it this with incremental solving. When SMS outputs the first graph, then we add another clause that excludes exactly this graph, and we just run again. We can use still reuse all the learned clauses. We can still use all the clauses that the minimality check has added, and build from there. And this is then very quick. So first, it might take longer to get the first graph, but then all the others are usually found within a small time.
And the timings that you gave, was that in order to get the results or to do the DRAT? Because often the DRAT takes a lot longer than.
Yeah, the times are reported here on the tables is without DRAT.
Thank you again, Stefan.